Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on calculating special functions, and in this lecture, I'm going to discuss the modified Bessel function. So previously, we discussed the original Bessel functions, which were the solutions to the Bessel ordinary differential equations. But now the modified Bessel functions are the solutions to the modified Bessel ordinary differential equations. And it's a second order differential equation. So we need two linearly independent solutions, which are denoted by I nu and k nu, and nu is the parameter of the differential equation. And when nu is an integer, in this special case, we denote the solutions by in and kn. So in is the modified Bessel function of the first kind, and kn or k nu is the modified Bessel function of the second kind. And the modified Bessel differential equation is x squared y double prime plus xy prime minus x squared plus nu squared is equal to 0. Now in the original Bessel function, if you recall, we had plus x squared minus nu squared times y. Here I have to add the y. There should be a y here. If we have minus x squared plus nu squared, all right? So the sign has flipped, and as you probably can guess, this means that there is some sort of imaginary number substitution is going on. So if we replace x in the original differential equation with jx, where j is the imaginary index, then we end up with something like this, all right? Now the I nu and k nu, they have integral solutions, which is not valid for all numbers. It's only valid for a range of numbers. And I nu, and these are very similar to the original Bessel functions, right? But the behavior has changed. I nu is 1 over pi integral from 0 to pi e to the x cosine of theta. So this is an exponential. And then cosine of nu theta d theta minus sine of nu pi over pi 0 to infinity e to the minus x cosh t minus nu t dt. And as you can see, this is only valid when this improper integral converges. So the condition for convergence is that the real of x is positive. All right, and we had a similar case for Bessel function itself. Let me see if I can find it. So for the ordinary Bessel function Jn, we had or J nu. Let's see, where was J nu? We had minus sine of alpha pi or nu pi over pi 0 to infinity e to the minus x sinh of t minus alpha t, right? And we said that it's only true when x is positive for real numbers. Now for complex numbers, we say that it's only valid when the real part of x is positive, all right? So the integral representation is only valid for the real part of x is positive. And plus calculating an improper integral from 0 and infinity is not very fast, very efficient. K nu, the same thing. We have 0 to infinity e to the minus x cosh of t, cosh of nu t dt, right? As you can see, I nu and k nu, nu appears in here, cosine of nu theta, and here and here. And for k nu, we have the nu only in here, cosh of nu t. And cosh or cosine hyperbolic is a even function, right? It has even symmetry. So k nu is an even number. I nu, it doesn't have a parity. It's neither even nor odd. But if nu is an integer, in, then sine of n pi is always 0, so we don't deal with this term. And then in of x is 1 over pi 0 to infinity e to the x cosine of theta, cosine of n theta d theta. And then this cosine of n theta is always even for n. So in also has an even parity for n. and k nu always has an even parity for nu because of this cosh nu t. All right, and the relation to Bessel functions, and again we have already implemented a very efficient ways of calculating the Bessel functions j and y, j nu and y nu. So if we have a relation between I nu and j nu, we can just implement I nu the same way as we implemented j nu. So I nu of x for any x, real, complex, doesn't matter, is this small j, which is the imaginary number. So let me just write it down here. This is imaginary number. Imaginary number. Okay. J to the power of minus nu, and then Bessel function nu jx. All right. And if you go back and look at the power series expansion that we had for the j nu of x, and if you substitute x with jx and then multiply it by j to the minus nu, we end up with this series for where did it go? We end up with this series for I nu. K from 0 to infinity, 1 over k factorial gamma of nu plus k plus 1, x over 2 to the power of nu plus 2k. And we know very well how to implement this numerically very efficiently. So we factor out a factor, we take out a factor of x over 2 to the power of nu. And then we also factor gamma of nu plus 1. And then we build a recursive calculation for the rest of the terms. So x over 2 to the power of nu is evaluated only once, which goes into the lead term. Gamma of nu plus 1 is also evaluated only once, which goes into the lead term, and the rest is just a multiplication of some double numbers, right? So k nu, it can be directly evaluated from I nu. So k nu is pi over 2 I minus nu of x minus I nu of x over sine of nu pi for non-integer, right? If so let me write this here. If nu is an integer, we take the limit here. So if nu goes to n, take the limit. All right, so we take the limit, because if we just set nu to n, sine of n pi is 0. I of minus n, I just mentioned that I of minus n is equal to I of n. So the numerator approaches 0, denominator approaches 0. So we end up with 0 over 0. And when we take the limit and the ambiguity and calculate the ambiguous value of the fraction, it's a number that determines the value of k nu. All right, so the general behavior of I nu, first of all, the general behavior of the Bessel functions jn and yn was oscillatory, right? And they resembled sine and cosine. And I just said that I nu and k nu are related to the Bessel functions by substituting x with jx. So if I substitute x with j of x in a sine of x function, I get sinh of x, sine hyperbolic, right? Sine and cosine becomes sine hyperbolic and cosine hyperbolic, all right? And sine hyperbolic and cosine hyperbolic are related to the exponential functions. So what happens here, we go from sine and cosine behavior in the ordinary Bessel function, or oscillatory behavior in the ordinary Bessel function, to exponential rise and fall in modified Bessel function. So Bessel function of the first kind, in, or in general I nu, it gets a rising exponential behavior with I0 starting from 1, because I0, basically I0 at x is j0 at jx, and when x is 0, both of them evaluate to 1, right? When nu is 0. So I0 at x is 1, and then it exponentially rises. I1, I2, I3, all the I nu, they start from 0 except for I0. and they exponentially go up. All right, and they never I believe they never cross each other, but we can check it later. And if I nu is exponentially growing, k nu is exponentially decaying, right? So k0, k1, k2, k3, they all are exponentially decaying, and after x greater than 5, 6, it basically becomes 0. All right, so how do we numerically implement these Bessel functions, these modified Bessel functions? Well, as I mentioned, we can, the first approach is to implement the integration, right? And it's very easy to do it for integer index when nu is integer, because this second term, which has an improper integral, vanishes, right? And then we end up with a very simple proper integral, 1 over pi from 0 to pi e to the x cosine of theta, cosine of n theta, d theta. And here's the code that I wrote. In takes an integer as the index or the parameter of the Bessel function, and then double x, and then func in is basically the integral function. I'm using a lambda expression, 1 over pi x of x cosine of t, cosine of nt, and t is basically the theta parameter of integration. And then our integrator class that calculates the integral, we set the integral function to func in, and then integral, I'm using Romberg and Simpson to accelerate the convergence from 0 to pi with some order, which can be 50, 100 or something. And then here I'm just plotting them. I create my modified Bessel function. X goes from 0 to 5, and remember in is exponentially growing, so if we go to, for example, from 0 to 10, we suddenly jump to a very large numbers. That's why I'm limiting it to 0 to 5. All right, and then we calculate I0, I1, I2, I3, and then create our MATLAB chart figure. I0 is blue, I1 is red, I2 is green, and I3 is K, which is black. And then we render it, set the X and Y labels, and then turn the legends on, and then show the plot, right? So this is the result, exponential growing. I0 starts from 1, and the rest of I's start from 0. So this is basically 1, all right? Okay, but then again, that integration is a very bad idea in terms of numerical efficiency, because we have to calculate this integral, and plus this is not applicable when basically x becomes a complex number, and or when nu is not a integer number, right? When nu becomes a non-integer value, and this improper integral doesn't converge for real of x negative. So this is not the best definition of I nu, right? So what we do, we go and try to do an efficient Java implementation, and this could be in general any nu. So instead of n, I say symbol I nu, all right? And here I nu, again, by definition, is j to the minus nu power j nu Bessel function jx, and we calculate like this. And again, the way we calculate this, we calculate the lead term first, and the lead term only depends on nu. And if you recall my lectures on the Bessel function j nu, we saw how to calculate the basically the lead term. The lead term is x over 2 to the power of nu. This comes out of the summation. And then we also factor out gamma of nu plus 1, right? That's what I'm calculating here. And again, we cache the value of the gamma nu, because if we are only sweeping the x values and nu is constant, we don't need to calculate this lead term, this gamma nu plus 1, basically many times, right? All right, so we make sure that we monitor the value of the nu, and we cache it in the state of the object, last nu and last gamma. And if this is not changing with some tolerance, we just update the lead term by using the last gamma. Otherwise, we update the last nu, we cache the nu again, recalculate the gamma again, and then calculate the lead term again. All right. And then again, the other thing is that when we do a recursive construction of the sigma, let me go back to the Bessel function, the ordinary Bessel function. As you can see, we said that the way that we have to formulate this kind of behavior x over 2 to the nu plus 2k over k factorial gamma nu plus k plus 1. So I nu is exactly like this, but we don't have this minus 1 to the kth power term. And this minus 1 to the k is just plus minus 1, right? So eventually, instead of having minus, 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 all of these become plus, plus, plus. And we factor out gamma 1 plus nu, and this lead term gets calculated only once, and we don't even need to calculate x over 2 each time, right? So again, the implementation is very similar to the ordinary Bessel function. So I nu sequence, we create our sequence that basically starts from 1 for I equals n, I greater than 0, I minus minus. Again, we calculate recursively. All these signs are now plus instead of minus. Val over I times R plus nu times result. And then we evaluate it at some, let's say 200 terms multiplied by the lead term. And again, going back to the summation, we don't, in the I nu, we have exactly the same thing, but we don't have this minus 1 to the k term. So all these negatives becomes positive. And then we start from the last term, the nth term. When we say we calculate from 0 to n, it means we drop n plus 1 and later. So the last parenthesis becomes 1 plus 0, which is 1. That's why we start from a result of 1. And then we recursively calculate backward to get all the terms, right? That's the reason that, where was I? That's the reason that we start from result 1 and recursively calculate backward. And notice these are just simple multiplications. So these calculations are very fast. The only time consuming was this lead term, because it has a power function and a gamma function. But if we basically cache it for the cases when only x is changing, we can just cache the value of nu and gamma, nu plus 1, and then it speeds up the process a lot. All right. And here's an example. I0, again, the blue curve starts from 1. I.5 starts from 0. I1, I2, I3. All right. And the key here is that in order to speed up the evaluations for a particular range of x and a fixed value for nu, we can cache the value of gamma nu plus 1 in the lead term when only x is changing. All right. This is the trick to make the evaluation very fast. Yes, as I mentioned, for any I nu, even for complex arguments, this equation still works, right? And again, if you recall, we also had a separate implementation for J nu when the argument was very large. But here, when the argument is, we typically don't deal with large arguments because this is an exponential growth. So after x greater than 7, 8, or 10, we end up with a very large number. So we typically are in this range from 0 to 5 when we are actually evaluating the I nu. And no need to use large arguments asymptotic. We can if we want to, but there is no real need to do it. And here's an example of calculating the I nu Bessel function. Nu is 0, and for a complex number x plus j, so I'm sweeping x, the real part, and the imaginary part is always j, right? And here's the code. So for complex numbers x, we have to be careful because based on the quadrant that the complex number is in, based on the sign of the real part or the imaginary part, there is some conjugations happening, and that's just because of how the phase behaves, how these series are derived for complex numbers. They always have some condition on the phase, which quadrants the complex number is in. But it's just a simple conjugation. So if the real part is negative, if the real part is positive, imaginary part is positive, we have the same equation here. Similarly, if the imaginary part is positive, regardless of the real part, we always have this number, this equation. If the imaginary part is negative, then we conjugate x and then conjugate the result again, something like that. And then for complex numbers. So this one was for double numbers, right? And this one is for complex numbers. So let's head to Eclipse and try to look at the implemented code. So in the special function package, I have this modified Bessel function integration, and in for int and double, we just do the integration, and in for alpha or nu for a double index or double parameter, we then need to calculate this improper integral. And then it has so the integral function func in infinity, t goes to 1 over pi x power minus x cosh of t minus alpha t, and we have to sum from 0 to infinity, which we limit it to, let's say, 100 or 50. I think the convergence is fast. All right, the same thing for kn, we can implement the integral. But then I have this modified Bessel function, which I actually implement the series representation, and this is supposed to be very fast evaluation, right? Especially the fact that when we are sweeping x, we're caching the gamma. And the assumption here is that we start from nu equals 0 and the last gamma is 1. And if nu changes, here we update the cached value of nu and gamma and calculate the lead term again. And I nu for double nu and double x, if nu is not an integer and x is negative, then I nu becomes complex. So that's why I have this condition to change. The first condition here tells me whether or not nu is integer, and I'm setting the 0.01 tolerance for this. And the second condition is x is negative. And we're saying that I nu becomes complex, so pass x as a complex number, and we're returning nan. All right. So let's look at the test class that I wrote. So let's see. Test. Do I have it? Test modified Bessel here. So let's look at some of the tests that I wrote. So in test 1, I create my modified Bessel function. This is based on the power series. I calculate from 0 to 5, 1000 terms. I time it, I0, I.5, I1, I2, I3, and I calculate them and then plot them. So let's run this. 22 milliseconds to do 5000 evaluations. So it's pretty fast, very fast. It's very fast, all right? And then we can export this to Python and compare it with the SciPy library. So I export it to a text file, and I open the text file in a text editor and copy all the numbers and all the lists here. I go to my Jupyter notebook and plot, and now I have x0, y0, xy, y1, x2, y2, x3, y3, x4, y4. All right. And then the next thing that I do, let me just make the figure large. All right. Here, x0, y0 with the color blue, and x0, and let's see, scipy.inu. All right. And then we're going to set 0 and x0. And as you can see, we have a good match. I believe I need to make the font larger. Let's see. All right. So, and the title is, so this is the I0, and then we have I.5, which is which is Y1. It starts from 0, and we have a good match. And Y2, which is I1, again it starts from 0 and goes up. Y3 is I2, again perfect fit, and y4 is I3, and again very good fit. All right, and of course we can plot all of them simultaneously. y0, y1, y2, y3. Okay, and we don't need to specify the color, so that it gets the automatic color here in the Jupyter notebook. Okay, and also y4. All right, and I'm going to change the color here to black, and we're going to copy and paste. Zero, 0.5, 1, 2, 3, and let's see. Okay, as you can see, we have a very good fit in all of the curves. So this shows that our implementation in Java based on the Power series was very good. It was really fast, and the same situation for the complex numbers, complex implementations. And you can write the code and verify that it matches very well to other libraries like SciPy. And for all the cases, the complex number could be in the first quadrant, second quadrant, third quadrant, and fourth quadrant. And if you do these conjugations based on when the imaginary part becomes negative, it's in a lower half plane, then you should always get the right sign for the real part and the imaginary part. So I hope you enjoyed this lecture, and I'll see you in the next one.